This video is going to cover just part of section 2.4. We are going to look at some rates of change and tangent lines in section 2.4, and we are just on the verge of getting into calculus. So everything we've done so far in all of your notes and homework, it's not calculus. So before we get to the calculus part, let me make sure that you understand the algebra part. And we're going to go we're going to jump back to Algebra 1 and talk about rates of change. So in Algebra 1 that you learned that slope was a rate of change, or maybe you learned it as average rate of change. It was just slope. And so in calculus, in this class, we are going to kind of talk about average rates of change versus instantaneous rates of change. So first of all, average rate of change, I'm going to abbreviate it AROC for average rate of change. So I don't have to write that out every single time. And all it is the how the y changed over how the x changes. So x is typically, if we have time involved, time is usually on our x-axis. And so we're looking at change in y over change in x. That's all it is, average rate of change. Change in y over change in x. So we're going to start out with this problem. And you did this in pre-cal at the very beginning of the year. And I remember this because I just made some pre-cal videos over it just yesterday. So it says find the average rate of change. We need to do slope. And we're going to use these two x values for our 2 points. So we've got two x's from x equals 1 to x equals 3. So our 2 points that we're going to put in our slope formula are 1 comma something and 3 comma something. I just didn't tell you what the y's were. But no problem, you're smart enough to figure it out. So let's plug this x value into our function and see what we get for y. And then let's plug our next x value, which is 3. Let's plug 3 into our function and see what we get for y. Now do slope. Average rate of change is just slope, which is y2 minus y1 over x2 minus x1. So what this is saying is this cubic function, if we only look at the cubic function from x equals 1 to x equals 3, on average, the average of the whole change from 1 to 3 was it went up 12, on average. Okay, and then we get into an application problem. So I would hate to be the one doing this experiment, but it looks like this is growth of a fruit fly population in a controlled environment or experiment. And you all know that it seems like fruit flies come out of nowhere. Like you have a banana in your house for a couple of days, and then all of a sudden there's a fruit fly, and then there's another one, and then there's another one. And you got to throw that banana away quickly and get it out of the kitchen, or else you're going to have a lot of fruit flies. Okay, so we start with about 0 fruit flies, and over the course of 50 days, look how the population of fruit flies increased. So you can see it was a slow increase at first, for the first few days, and we start picking up a bit, and we start picking up again a bit, and then I think that right around here it was the population was growing very quickly. Quick increase, right? And then long around, I don't know, day 35 or 40-ish, it kind of slowed up a little bit. Still, the population was still growing, but not as fast. And then we end up with close to 350 fruit flies at the end of our experiment. So what we're going to do in calculus is we're going to look at how fast were they growing. Well, right here they weren't growing, the population wasn't growing very fast. Faster, fastest, not as fast, not very fast at all. Okay. So, the example wants us to do average rate of change from day 23 to day 45. On average, how fast was the population growing? On average. So, the math involved is super easy. I'm asked for average rate of change, which is just slope. Now hang on, let me clarify that. It's slope of a secant line. So a secant line is a line that touches the function more than once. So this secant line passes through this point, the one I'm looking at, and this point, secant line, it passes through twice. That's the line that I'm finding the slope of. So average rate of change is actually slope of our secant line. Okay. Important vocabulary that's going to come up later when we start doing some calculus. Slope of our secant line, I'm just going to go 340 minus 150 all over 45 minus 23. Gives me 190 over 22, so about 8.636. Now, take a minute. I'm going to ask you to put units on your answer. Think about what our Y's represent, fruit fly population. Think about what our X's represent, time in days. So this is fruit flies per day. So on average, from day 23 to day 45, we can say that the average increase was like 8.6 flies per day. Did it increase 8.6 flies every day? Oh, no. Here, I think the growth rate, the rate of change was considerably steeper than 8.6. This slope is 8.6 all the way along it. 8.6, constant slope. This, steeper, not as steep. So I think the growth rate along day like 23, like 25, 26, 27, faster than 8.6 flies per day. But up here, closer to day like 40, 41, 42, not as fast as 8.6 flies per day. We found just the average growth rate. So that's all we're doing for today is average rate of change. Pretty easy. You're just doing basically slope of a secant line over and over and over again.